Chapter 9, Advanced Linkage Analysis. What is genetic linkage analysis? Genetic linkage analysis is a statistical method that is used to associate functionality of genes to location on chromosome. So the main idea, neighboring genes on chromosome have a tendency to sit together and pass on to offspring. Therefore, if some disease is often passed to offspring along with specific marker genes, then it can be concluded that genes which are responsible for the disease are located close nearby on the chromosome to these markers. So as you can see, this is a DNA. Locus is where the allele are all together in one level. So you have allele for dominant, allele for recessive, they are on the same locus. And then these alleles, interaction between them is the genotype, and they will cause phenotype to appear. So there is the relationship. Class example for eye color. Eye color is the locus. In eye color, you have two alleles, brown and blue. So for a person who is homozygote, genotype is brown. So you have brown. For heterozygote, the genotype is brown-blue, but the phenotype is still brown because brown is dominant. And then you have somebody with blue eyes. It is because of the homozygous recessive allele for blue. So blue, you have blue eyes. Sex-linked allele. Most human cells contain 46 chromosomes, 2 sex chromosomes X and Y, XY in males, XX in females. The other two pairs are autosomes. Around 1,000 human alleles are found only on the X chromosome. Recombination inhibition. Recombination between X and Y chromosome prove harmful, resulting in males with unnecessary genes formerly found on Y chromosome and females with unnecessary or even harmful genes previously only found on the Y chromosome. As a result, genes beneficial to males accumulated near the sex-determining genes, and recombination in this region was suppressed in order to preserve this male-specific region. Over time, the Y chromosome changed in such a way as to inhibit the areas around the sex-determining genes from recombining at all with the X chromosome. As a result of the process, 95% of the human Y chromosome is unable to recombine. Only the tips of the Y and X chromosome recombine. The tips of the Y chromosome that could recombine with the X chromosome are referred to the pseudo-autosomal region. The rest of the Y chromosome is passed down to the next generation intact. It is because of this disregard the rules that the Y chromosome is such a superb tool for investigating recent human evolution. Because the Y chromosome only experiences recombination with the X chromosome at the ends, as the crossing over, the Y chromosome essentially is reproduced by cloning from one generation to the next. This prevents the mutant Y chromosome genes from being eliminated from the male genetic line except by inactivation or deletion. Consequently, the Y chromosome now has few active genes and mostly contains genetic junk than genes. Chimpanzees, our closest living relatives, have been on a separate evolutionary path from humans for only 6 to 7 million years. Subsequently, we still share most of our genes. We differ by only 1 to 2% in terms of DNA sequences. However, the genes on the Y chromosome are a major exception. The DNA sequences on Y chromosomes of chimpanzees and humans differ by 30%. Indicates that Y chromosomes have been evolving at a much faster rate than the X or all the other chromosomes. So, the medical perspective. When studying rare disorders, 4 general patterns of inheritance are observed. Autosomal recessive, such as cystic fibrosis, it appears in both male and female children of unaffected parents. So it is just like what you have learned in the Mendel chapter. Autosomal dominant, such as Huntington disease. Affected male and female appear in each generation of the pedigree. Affected parent transmits the phenotype to both male and female children. And then you have X-linked, X-linked recessive, and X-linked dominant. X-linked recessive causes many more males than females to show the disorder. All the daughters of an affected male are carriers. None of the sons of an affected male show the disorder or are carriers, because they only have X and Y. If the X that they have is a normal X, then they do not have any disease. They do not even carry the disease. But for women have XX. If one of the chromosomes are diseased, the other is normal from the mother, so they are carriers. X-linked dominant. Affected males pass the disorder to all daughters but none to their sons. Because fathers have X and Y. If they pass the X to the if they pass the X down, it is only for daughters. For sons, he will only pass down the Y chromosome. So Y chromosome doesn't carry the gene, meaning that the sons will be okay. Affected heterozygous females married to unaffected males pass down the condition to half the sons and daughters because she has two X's. So one X can go to the male, one X can go to the female. Example: after the disease is introduced to the family in generation 2 by that guy, it appears in every generation, so it is dominant. Fathers do not transmit the phenotype to their sons. As you can see, one generation is just male, and then the other generation below it just female, and then one generation below just male. So you can see just male or female in each generation. So you can say that it is X-linked. Sometimes in meiosis, homologous chromosomes exchange parts in a process called crossing over or recombination. Recombination fraction. The probability theta for recombination between two genes is a monotone non-linear function of the physical distance between the loci on the chromosome. So linkage 0 is smaller than theta. P recombination will be lower than 0.5. So meaning that theta would be the linkage. Recombination, if it is lower than 5%, if it is lower than 0.5, no linkage. The further apart two genes on the same chromosome are, the more likely it is that recombination between them will occur. Two genes are called linked if the combination fraction between them is small. So it is 50% chance. They are homologous pair, AA, BB, and then they cross over. When they cross over, you can see that the legs have a change. Now you have big A, big B, big A, small b, small a, big B, and small a, small b. So the middle ones are the recombinants. So interference. Interference means crossover in one region decreases probability of crossover in an adjacent region. So 1 centimorgan is the distance between the genes for which a recombinant frequency is 1%. Plot score is a method to calculate linkage distances to determine the distance between genes. The ultimate goal for this is linkage mapping. With the following few minor problems, it is possible to make control crosses in humans, and human offspring are rather small. One mother can give birth to how many children? Not more than 10. Okay, some people they only have 2 children or just 3. Okay. But the human genome, by comparison, it is immense. So there's a lot of data in it. The distance between genes are large on average. So it is kind of like trying to shoot at meteors. Okay, you will always miss unless you calculate it, because there's a vast distance between each and everything. Possible solutions. First is to make general assumptions. How do we make equilibrium? So in this HW equilibrium, it assumes that certain probability for a certain individual have to be a certain genotype. Liquid equilibrium, it assumes two alleles at different loci are independent of each other. So we put this assumption into possible solutions: Elson-Stewart method or Landry method. So in the Elson-Stewart method, so the input, you put the simple pedigree and the phenotype information about some of the people. So these are the people we call them type. In a simple pedigree, there is no cycles, just a single pair of founders. So founder, get a leaf. On that leaf, you get, who do you get? The output, probability of the observed data, given some probability model of the transmission of alleles. It is composed of founder probabilities, RDO equilibrium, penetrance probabilities, probability of the phenotype given the genotype, transmission probabilities, which is probability of the child having a certain genotype given the parent's genotype. Bottom up, it is a sum condition probability of all possible genotypes of children, only then one possible genotypes of the parents. So it is linear in the number of people. Now this is another method called the Landry method. Landry method computes probability of marker genotypes given an inheritance vector. We have P, M, I, V, I, and locus I. So Mi is the marker data in the locus, which is your evidence. Pi is a certain inheritance vector. The main idea: let A1, A2 until A to F be vector of alleles assigned to founders of the pedigree. F is the number of founders. We want to graph representation of the restrictions imposed by observed marker genotypes on the vector A can be assigned to the founder genes. This algorithm extracts only vectors A compatible with the marker data. So PR M B is obtained via a sum of all compatible vectors A. So marker data on pedigree, you have 1, 2. Just imagine that there is a 0 behind the 1. 0, 1, 0, 2, meaning that they are the parents. Then 1, 1, 1, 2, 1, 3, 1, 4. Generation 1. Individual 1, 2, 3, 4. Then 2, 1, 2, 2, 2, 3 to 4. They are all generation 2. Individual 1, 2, 3, and 4. Okay, so if you look at the marker data, you have A and B. Individual 1, 2, and 1, 3. Because they actually form the same parents. Parent 1 and parent 2, they have A and B. Right, so this person 1, 2 marry with 1, 1. Then you get children 2, 1 and 2, 2. So you have AB, AB, AB. Meaning that the marker data is still intact. But person 1, 3 marry with 1, 4. And then suddenly the children has AC and BD. So where did the C and D come from? C and D come from person I4. Person 1, 4. Person 1, 4 carries the C, D alleles, which are locus to B and A. Right? So this is the descent graph. It corresponds to specific inheritance vector. So the vertices, the lines, it is the individual genes, 2 genes for each individual in the pedigree. The edges represent the gene flow specified by inheritance vector. Child's gene is connected by an edge to the parent gene from which it flows. Descent graph by Sobel and Lang 1996. Our pedigree consists of both paternal and maternal allele for each individual as its vertices, and one link between parent-child pairs as it ages. Each age specifies which of the 2 alleles of parent is transmitted to a child. A descent graph illustrates one possible inheritance pattern within the pedigree, and by definition, it does not include genotype information. So, as you can see, on the left, it is a pedigree. You can see, normally the woman marries the man, and they have the children. Children, who do they marry? Right. But the descent graph is different. In B, you can see that you have allele. Each one of the allele would be going to one person and then on one person. As you can see on top, there's 2 dots. That 2 dots signify one person. That one person has 2 alleles. She or he will give the allele into one of his children. Okay, so one child would get one allele from each parent, from the mother and from the father. And there you can see the graph of descent. Okay, and the allele goes from the father to son. Okay, and then from the son to his daughter. Okay, and then it goes around again. But as you can see in that picture there, all of it kind of converges into one. So the person on the bottom, which is person number 11, are actually having parents who are related. How related are they? Because the alleles can actually come from the same ancestor. So we can call them IBD, identical by descent. They descend for the same ancestral allele. So if you want to compare with pedigree, this one is much easier because you know from where the alleles come from. Okay, so from here, what can you see? On top is the pedigree. So pedigree, you name each person based on the tier, based on the individual. Tier 0, 0, 1, 0, 2. Tier 1, 1, 1, 1, 2, 1, 3, 1, 4. Tier 2, 2, 1, 2, 2, 2, 3, 2, 4. Okay, for the descent graph, there's supposed to be a line here. Okay, there's the line. Assume that paternally inherited genes are on the left. Assume the non-founders are placed in increasing order. Non-founders meaning that people who are not from the family. Okay. So, 1 bracket 0 is used to denote paternally and maternally originated gene. So, gene plot above correspond to the inheritance vector B1100 11 11 11 0. Right. So if you look at that number 1 is paternal, 0 is maternal. So 1 1, why does this person have 1 1? That gene is from the maternal, because the gene is from a paternal source. So 1 1 0 0, both are from maternal. 3 and 5, they give each own allele to the children. So we have A and B. Next will be 0 0. Right there. Why is it 0 0? Because both of these alleles are from maternal origin. So 3 4 5 6. Right. If you look at this person, these two persons, one allele is from the father, one allele is from the mother. So the person who is the first, the one that is in the middle there, so they get the father allele from both mother and father, so paternal. So it is paternal 1 1. The second person there, who get the allele from 4 6, 4 and 6 are both maternal allele, so maternal 0 0. Next. Okay. And so this person right here gets the paternal allele. First one is from the 3 and the other from the 1. So paternal 1 1. This next person also, the person also gets the paternal gene from the person above, who gets it from 3, and the immediate parent who get it from 1. So both genes are paternal. They come from a paternal or male ancestor. So 1 1. Same goes here. Also getting the allele from the paternal source 7, and also this person right here is different because he got the allele from the maternal source. So from 4, it is a maternal gene 4 4 4, and then the other allele comes from the 7, which is also a maternal gene, so 0 0. So here you can see the descent graph. So for descent graph will be, where does the allele go down from, which is A and B. And then in the founder graph, what you can see, these are the founder, or where does the gene originate from. So it's 5 and 3. 5 and 3 gave the genes to who? 2 and 1. Then 6 and 4 are both maternal. 8 and 7 also maternal. So you can see 5 and 3, A and B. So 3 to 1 also A and B. 6 to 4 will give A and B allele, but in person 7, this person 7 has given a new allele, which is C. So it's connected there. Then 6 and 8, they are connected through this bridge from B to D, because the person on the right gave 2 alleles, 7 and 8. So C and D. So B and D are connected by the number 8. So you must find a compatible allele assignments for non-singleton component. That's why you have to identify some compatible alleles for each vertex. So compatible allele each vertex is the intersection. AB crossover with AB. So who has it? Person 1, 3, and 5. So what about AB and BD? What is the crossover? Crossover is B. So AB, BD, that's the crossover. So for the ground component 2, you have Elliott assignment A, B, C, and D. For ground component 1, 3, 5, Elliott assignment A, B, A, B, A, B. And then 4, 6, 7, 8. Okay, how are they connected? F, A, B, C, and D. So comparing P and B. If for some component there are no possible Elliott assignments, then P and B is 0. Probability of singleton components is 1, we can ignore them. Let AHI be an element of vector of Elliott assigned to the vertices of the component CI. So superlink. Superlink combines all of the approaches into a unified program. It has built-in capabilities that can increase the computation ability. It can be more capable and faster than the other related programs by its own makers. In this link, mapping human genes by linkage analysis. Linkage analysis is a method that is also used to decide if two loci or a loci in this gene are linked. So we ascertain whether the combination fraction theta between two loci deviates significantly from 0.5, and if it is different from 0.5, we need to make the best estimate of theta, since the parameter tells us how close the two linked loci are. Lineage is expressed as a log score z of a logarithm of odds. Log score theta, it is equal to log 10 likelihood of linkage over likelihood the loci are not unlinked. So theta 0.5. Positive value of z at a given theta suggests that the two loci are linked. Negative value of z at a given theta suggests that two loci are not linked. By convention, a log score of 3 and greater is considered definitive evidence that the two loci are linked. A log score below -2 excludes the linkage. Probability of recombination is theta. N is the amount of recombination in pedigree. Probability that no recombination will occur is 1 minus theta. M is the amount of non-recombinant in the pedigree. So z theta log 10 theta n over 0.5 over n plus log 10 for the non-recombinant. So combine together, you can get the equation on the right. Log 10 theta n and then times 1 minus theta m over 0.5 to the power of n over 5 to the power of m. So here, locus 2 RP9. Exercise. Calculate log score theta 0 at a similar family with 10 children without any connection between disease locus and the marker. So what's the number that you will put? So the n is what? 10. The m is 0. RP9 is the disease allele in locus 1. If you can see recombination happen, recombination will cause this allele to move to the different chromosome. Instead of big A, you go to small a. So where can you see it? You can see in children number 2. In child number 2, the disease allele RP9 is detected with small a instead of big A, meaning that recombination actually happened. But what about the others? The others is still the same. Big A with the disease. Small a, small a, small a, no disease. Okay, so what number do you enter? 1 and 5. Okay, so answer is minus infinity. So what about we calculate log score for theta 001, 0.01, 0.1, 0.2, 0.3, 0.4 and 0.5? What will you get? So if the theta is 0, log score will be infinity. But if it is 0.01, that's the log score, 1.19. Okay, so at 0.1, the log score is 0. Interpreting log plots. Now we have family A and family B. So family A, this man has the disease and the woman doesn't. And then they marry, and then the daughter have the disease. The daughter with the disease marry with a man who is normal, and then you can see of all 3 children, 2 get the disease. One is a male, one is the female. Alright, so in A, we actually know the phase. So if you have big D, big M, small d, small m, it is a non-recombinant. What about the children? Big D, small d, big M, big M. Big D, small d, big M, big M. So where did the recombination happen? Recombination actually happened between the M alleles in the M locus. So if big D, big M slash small d, small m, it is recombinant. But if it is big D, small m, small d, big M, then you know that it is a recombinant. What about B? In B, you can see that it is big D, everything is known, but there is the phase which is unknown. You have big D, big M, small d, small m, non-recombinant. So from this, what can you gather? You can gather that in B, among the 3 children, the D and M actually did not recombine, because you can see that big D, B and big M, it is there, just like the mother and also the grandfather, in that here in all 3 phases there is no recombination. So this is a log score for various values of theta. The end. Continue in part 2.